Hello there, and welcome to the Sleeping Physicist. If you're someone who likes to unwind by thinking about stars, particles, and the quiet structure of reality, you're in the right place. Tonight, we'll let our attention drift gently into real physics and real discoveries. Some of what you'll hear may sound surprising, but all of it is real. And if you enjoy these slow journeys into how the universe works, you're always welcome to like and subscribe. But for now, settle in. Let your body rest, let your thoughts soften, and let's begin. What is mass actually made of according to quantum field theory? Before that question becomes abstract, it helps to notice how mass first enters our lives. You feel it when you lift a mug from a table and your arm senses resistance. You notice it when a bicycle takes effort to start moving and even more effort to stop. Mass shows up as heaviness, as stubbornness, as the simple fact that objects do not like to change what they are doing. When something has more mass, it presses down more strongly, it accelerates more slowly, and it carries momentum that is harder to redirect. These are not ideas from textbooks. They are experiences your body has known for as long as it has moved through the world. After noticing that, it becomes natural to ask where that resistance comes from. When you hold something solid, it feels as though mass must be a kind of substance packed inside, like sand filling a container. But when you look closely, there is nothing you can point to inside an object and say, "This is the mass itself." You can see atoms arranged in patterns, and even those atoms are mostly empty space. And yet, the resistance remains. The weight does not disappear when you imagine the emptiness. That is the first quiet clue that mass may not be a material ingredient at all, but something that emerges from how matter behaves when it moves. Wherever you are, the same physical law applies. Mass resists change. It does so reliably, predictably, and everywhere in the universe we have measured it. And that consistency tells us something important. Whatever mass is made of, it is not an optional feature or a surface detail. It is woven into how the universe responds when energy tries to flow and motion tries to change. This is why physicists began to suspect that mass could not be explained by piling up smaller and smaller pieces of matter. The resistance you feel is not coming from hidden grains or internal weight, but from something more fundamental, from the way reality itself reacts when pushed. Once you follow that idea carefully, it leads inevitably away from solid building blocks and towards something quieter, more subtle, and far more pervasive. Even though mass feels solid and dependable, it does not present itself as something you can see or isolate. You never encounter mass on its own. You encounter objects moving, pushing, resisting, falling. Mass reveals itself only through behavior. It is known by what it does, not by what it looks like. This is unusual, because most things we think of as being made of something can be pointed to, divided, or held up as an example. Mass refuses that kind of inspection. If you imagine taking an object apart piece by piece, you can separate its materials, identify its atoms, and even break those atoms down further. But at no stage do you uncover a nugget labeled mass. Instead, what you find are smaller structures still behaving as though they possess inertia. They still resist acceleration. The property survives every layer of inspection. That persistence tells us that mass is not hiding inside matter like a component, but is instead a rule that matter follows. A helpful way to picture this is to think of mass less like cargo and more like drag. When you move your hand through water, the resistance you feel is not something stored in your hand. It comes from how the water responds to motion. The resistance exists only when movement is attempted. In the same way, mass begins to look less like a thing an object contains, and more like a response the universe gives when that object is pushed. This shift in perspective matters because it changes the question we are asking. Instead of wondering what substance mass is made of, we begin asking what conditions cause resistance to motion to appear at all. What underlying structure of reality makes motion costly, acceleration difficult, and change gradual rather than instant? Once the question is framed that way, it points away from visible matter and toward the deeper framework that governs how matter exists in the first place. That framework is not built from objects but from something more continuous and ever-present, something that does not sit inside space but fills it completely. And following that idea carefully leads us to the modern view that beneath particles, beneath atoms, and beneath even the idea of solid matter, there is a quieter foundation made of fields rather than things. That idea of an ever-present foundation becomes clearer when we notice a quiet problem with the picture of particles as tiny solid dots. If particles were truly little objects moving through empty space, then mass would have to be something glued onto them, an extra feature carried along as they travel. But experiments kept revealing that particles behave less like objects and more like events. They appear, disappear, interfere with themselves, and spread out as probabilities. The deeper physicists looked, the less sense it made to think of particles as the fundamental ingredients of reality. What we call a particle is not a tiny bead, but a small, localized excitation in one of these fields, like a ripple briefly rising and falling on a vast, invisible surface. Once this shift is made, mass stops looking like something carried by particles and starts looking like something encoded in the behavior of fields themselves. A field can respond to energy in different ways. Some disturbances move effortlessly, while others resist change and require extra energy to accelerate. That resistance is what we interpret as mass. It belongs not to a particle as a thing, but to the field as a pattern of response. An analogy can help here, briefly and carefully. Imagine a stretched fabric filling a room, even though you cannot see it. A quick flick of the fabric sends a wave racing across it with ease. But if part of the fabric is thick or strongly coupled to its surroundings, moving it takes effort. The resistance is not an object hidden in the fabric. It is a property of how the fabric responds when disturbed. In quantum field theory, mass plays a similar role. It describes how stiffly a field reacts when energy tries to make it change. Seen this way, the universe no longer feels like a collection of heavy things floating in emptiness. It feels more like a continuous system with different ways of responding to motion and energy. Some responses are light and swift, others are slow and resistant, and mass emerges naturally from those differences, not as a substance but as a behavior written into the fields that quietly occupy all of space. To understand that response, it helps to slow down and become familiar with what a field really means in physics. A field is not an object sitting somewhere. It is a condition that exists at every point in space, whether or not anything obvious is happening. Temperature is a simple, everyday example. Even in a quiet room, every location has a temperature value, whether you measure it or not. A quantum field works in a similar way, except instead of describing warmth or cold, it describes the potential for particles to appear and interact. Each quantum field fills the universe completely. There is an electron field everywhere, a quark field everywhere, a photon field everywhere. Most of the time, these fields are calm, resting in their lowest energy state. But when energy flows through them in the right way, a small, localized disturbance forms. That disturbance behaves exactly like what we call a particle. It has a position, it can move, it can collide, and it can transfer energy. But fundamentally, it is a temporary pattern in something that was already there. This perspective quietly dissolves the idea that empty space is truly empty. Even in the deepest vacuum, far from stars and atoms, the fields remain. They fluctuate gently, constrained by quantum rules, never fully at rest. What we experience as matter is simply a particular way those fields are excited and organized. The solidity of objects comes from countless overlapping field disturbances interacting in stable, repeating ways. Once you see fields as the primary reality, mass begins to look less mysterious. A field can be easy to disturb or hard to disturb. Some fields allow their excitations to move freely at the speed of light. Others resist change, requiring extra energy to create motion or acceleration. That resistance is not added afterward. It is part of the field's identity, woven into how it exists in space and time. So when we ask what mass is made of, quantum field theory answers in a surprisingly gentle way. Mass is not built from smaller pieces. It is not stored inside particles. It arises from how a field responds when energy tries to set it into motion. And once that idea is in place, we can begin to see how mass is mathematically and physically encoded in the behavior of fields themselves, long before we ever notice a particle at all. With that foundation in place, mass can finally be seen in its proper context. In quantum field theory, mass is not an added feature that fields acquire later. It is built directly into how a field behaves when it is excited. When a disturbance forms in a field, the rules governing that field determine how much energy is required to create it, how easily it can move, and how strongly it resists acceleration. Those rules are what we experience as mass. Some fields allow their excitations to glide effortlessly. Once created, they move at the universal speed limit and cannot slow down or speed up. Light behaves this way because the electromagnetic field has no built-in resistance to motion. Other fields behave very differently. Creating an excitation in them already requires energy, even when nothing is moving. And when you try to accelerate that excitation, the field pushes back. The more you try to change its motion, the more energy it demands. That demand is mass revealing itself. This means mass is not something sitting inside a particle. It is a relationship between energy and motion dictated by the field itself. A massive particle is simply an excitation that cannot exist without a certain minimum energy and cannot change its motion without paying an energetic cost. The mass tells you how steep that cost is. A single analogy can help anchor this idea. Imagine walking across a frozen lake versus walking through deep snow. On the ice, once you start moving, you slide easily. In the snow, every step resists you. The resistance is not something hidden inside your body. It comes from how the surface responds to motion. In quantum field theory, different fields are like different surfaces. Some offer almost no resistance. Others respond in a way that makes motion heavy and costly. Mass is the measure of that resistance. Seen this way, mass becomes inseparable from dynamics. It only shows itself when something tries to move or change. When a field excitation sits still, its mass is quiet but still present as stored energy. When it accelerates, that mass becomes active, shaping how the excitation responds. And this prepares us to understand why one particular field, discovered only recently, plays a unique role in setting the mass of many particles in the universe. Among all the quantum fields that fill space, there is one whose behavior stands out in a crucial way. Unlike most fields, which settle into a calm, neutral lowest state, the Higgs field does something unusual. Even in its quietest condition, it does not vanish. It maintains a constant presence everywhere, like a background that never quite turns off. This matters because other fields must exist within that background. As their excitations form and move, they interact with the Higgs field whether they intend to or not. For some of them, that interaction is gentle and barely noticeable. For others, it is persistent and strong, and it is this interaction that gives certain particles their mass. To picture this carefully, imagine space not as emptiness but as a medium with a built-in texture. Some excitations pass through almost without noticing it. Others continuously engage with that texture, drawing energy simply to exist and even more energy to move. The Higgs field provides that texture. It does not push particles down or slow them by friction. Instead, it alters how much energy is required for their fields to change over time. When a field couples to the Higgs field, its excitations gain a kind of built-in inertia. They can no longer behave like effortless waves. Even at rest, they carry energy. When accelerated, they resist change. That resistance is precisely what we measure as mass. The Higgs field does not supply mass as a substance. It sets the conditions that make mass unavoidable for certain fields. This idea was not speculation, it was confirmed when physicists observed a specific excitation of the Higgs field itself, the Higgs boson. Its discovery showed that the field is real, measurable, and woven into the structure of space. But even with that confirmation, the deeper insight remains quiet and subtle. Mass arises not because particles are filled with something heavy, but because they exist in constant interaction with a field that permeates everything. And yet, as central as the Higgs field is, it does not tell the whole story. In fact, most of the mass you encounter in everyday objects does not come from the Higgs field at all. To understand where that mass truly comes from, we need to look at how energy, motion, and confinement behave inside the smallest building blocks of matter. Once you look inside ordinary matter, a surprising fact emerges. The mass of familiar objects does not mainly come from the Higgs field at all. Protons and neutrons, which make up nearly all the mass of atoms, receive only a small fraction of their weight from the Higgs mechanism. Most of their mass arises from something more dynamic and more restless, happening deep inside them every moment. Inside each proton and neutron, quarks are confined by the strong nuclear force. They are never at rest. They move rapidly, exchange force-carrying excitations, and remain tightly bound in a small region of space. This confinement traps enormous amounts of energy, and according to the most reliable relationship we have between energy and mass, that trapped energy counts as mass. Here, mass emerges not from a background field setting inertia, but from motion itself. The quarks inside a proton are so energetic and so strongly constrained that their activity contributes far more to the proton's mass than the intrinsic masses of the quarks alone. What feels like solidity and weight at the macroscopic level is, at its core, the pressure of energy refusing to disperse. A single analogy can help clarify this without replacing the physics. Imagine air sealed tightly inside a rigid container. The container feels heavier not because the air has gained substance, but because energy has been confined. Pressure builds, resistance increases, and the system as a whole responds more stubbornly to motion. In a proton, the confinement is far more extreme and the energy far greater, but the principle is the same. This reveals something quietly profound. Mass can arise from interaction, from motion, and from constraint. It does not require a material ingredient beyond energy organized in a particular way. The proton is heavy, not because it is filled with stuff, but because it is a storm of quantum activity that cannot escape. And once that is understood, mass begins to look less like a fundamental property handed down from the beginning of the universe, and more like an emergent result of how energy behaves when fields bind, fluctuate, and refuse to let go. That idea leads naturally to one of the most quietly powerful insights in modern physics. Mass and energy are not separate categories. They are two ways of accounting for the same underlying quantity. When energy is free to move, it appears as motion or radiation. But when energy is trapped, circulating, or confined, it shows up as mass. Inside composite particles like protons, energy has nowhere to go. The strong force binds quarks so tightly that separating them would require more energy than simply creating new particles. As a result, the energy remains locked in motion, vibration, and tension within a tiny region of space. From the outside, that trapped activity appears as weight and inertia. The proton resists acceleration because accelerating it means accelerating all of that internal energy at once. This means mass can emerge even when the constituents themselves have very little intrinsic mass. What matters is not what the parts are made of, but how much energy is involved in keeping them bound together. The tighter the confinement and the more intense the activity, the greater the mass of the whole. Mass becomes a bookkeeping of energy that cannot escape. A careful analogy can help anchor this. Think of a tightly coiled spring sealed inside a box. The spring adds weight to the box, not because it contains more material, but because energy has been stored in a constrained form. That stored energy contributes to the box's resistance to motion. In the quantum world, particles like protons are less like springs and more like constantly vibrating systems, but the principle remains the same. Energy that is confined contributes to mass. This understanding dissolves the idea that mass must originate from some fundamental heaviness built into matter. Instead, mass emerges wherever energy is forced to remain localized and organized. Fields interacting, particles confined, motion constrained. All of these situations produce inertia. All of them produce mass. And once mass is seen this way, as energy held in structure rather than substance, it becomes possible to take one final step, to recognize that mass is not a static feature of reality at all, but an ongoing process that depends on relationships, interactions, and the rules governing how fields behave over time. When all of this is taken together, mass stops looking like a static attribute and starts to resemble an ongoing activity. It is not something matter possesses once and for all. It is something that is continuously produced by interactions happening at every moment. Fields responding to fields, energy circulating under constraint, motion being resisted not by substance but by structure. A particle does not wake up each moment carrying a fixed lump of mass inside it. Instead, its mass is renewed constantly by the rules that govern how its field can change. If those rules were different, the same excitation would behave differently. It would accelerate more easily, require less energy to exist, or perhaps not form at all. Mass depends on relationships, not ingredients. This is why mass can change under extreme conditions. Heat something enough, and its total mass increases slightly, because additional energy is now confined within it. Bind particles together tightly, and the combined system may weigh less or more than its parts depending on how energy is rearranged. These are not tricks or exceptions. They are signs that mass is bookkeeping for energetic processes, not a permanent label. Seen this way, the universe becomes quieter and more fluid. What feels solid is actually busy. What feels heavy is active. What feels permanent is being maintained moment by fields doing exactly what their equations allow, and no more. Mass is not a thing sitting still. It is a behavior sustained over time. And once that perspective settles in, it naturally reshapes how we think about matter itself. The table in front of you, the ground beneath you, even your own body, are not collections of heavy pieces. They are regions where fields are interacting in stable, persistent patterns, generating resistance to change through their motion and constraint. Understanding that brings us back, gently, to the world we started from, now seen through a deeper and calmer lens. With mass understood as a dynamic process, our picture of matter quietly changes. Objects no longer appear as collections of tiny heavy pieces stacked together. Instead, they become stable arrangements of activity. What gives matter its firmness is not solidity in the traditional sense, but consistency. Fields interacting in the same way, over and over, without drifting apart. When you press your hand against a table, you are not meeting a wall of substance. You are encountering an organized resistance produced by electromagnetic fields holding atoms in place, by confined energy inside protons and neutrons, and by the mass that emerges from those interactions. The table pushes back because changing its state would require rearranging an enormous amount of structured energy all at once. This explains why matter can feel both rigid and fragile. A diamond resists deformation because its internal interactions are extraordinarily tight and symmetric. A sheet of paper bends easily because its internal structures allow motion along certain directions. In both cases, mass is present, but how that mass participates in interaction determines the material's behavior. The difference is not in what matter is made of, but in how its fields are arranged and constrained. Seen through this lens, everyday objects are not passive. They are actively maintaining their form. Every moment forces balance, fields respond, and energy remains bound in patterns that hold together just long enough to be useful. Matter persists not because it is inert, but because it is dynamically stable. This view brings a certain calm clarity. The world around you is not frozen or fixed. It is continuously happening. What you experience as touch, weight, and resistance is the present expression of quantum fields behaving exactly as they must. And understanding that does not make matter feel less real. It makes it feel more intimate, more alive in its quiet persistence. From here, only one step remains: to allow this physical understanding to gently widen into a reflection on how the universe itself is structured, not as a collection of things, but as an ongoing, lawful interplay that gives rise to everything we experience. When this understanding is allowed to settle, a quiet implication follows almost on its own. The universe is not built from solid things placed into empty space. It is built from relationships that persist, fields filling all of space, interacting according to precise rules, giving rise to patterns that endure long enough to become atoms, planets, and bodies. Mass, in this picture, is not a primitive ingredient added at the beginning. It is a consequence. Wherever energy becomes organized, confined, and required to move, as a whole, mass appears. Wherever interactions stabilize into repeating structures, resistance to change emerges naturally. The universe does not decide where mass should exist. It allows it to arise wherever the conditions demand it. This means the distinction between matter and energy is softer than it once seemed. What you experience as material presence is energy behaving in a disciplined way. Not chaotic, not free, but held in balance by the laws governing fields. The universe is not filled with objects so much as it is filled with ongoing agreements between forces about how motion may proceed. There is something quietly reassuring in this. Nothing heavy is imposed from outside. Nothing solid is frozen into place. Everything that has weight has earned it through interaction, through motion constrained, through energy shared, through fields responding faithfully to one another, moment after moment. And so, when you feel the pull of gravity or the resistance of an object in your hand, you are not encountering dead matter. You are encountering the present state of an active universe, expressing its structure through mass. Not as a thing, but as a process that continues, patiently and reliably, wherever the rules of quantum fields allow it to exist. From here, the idea of mass continues to unfold without changing direction. If mass arises from interaction, then it depends on context. Change the environment a field exists in, and its effective mass can change as well. Physicists see this clearly in extreme settings, inside dense stars in high-energy collisions, or in the early universe. Particles do not behave as they do in calm, empty space. Their masses shift subtly because the surrounding fields and energies alter how resistance to motion is expressed. This tells us that mass is not just dynamic in time, but relational in space. It depends on what a field is interacting with, how strongly and under what conditions. A particle's mass is a summary of all those influences at once. It is the net result of how difficult it is for that excitation to change its state within the environment it inhabits. This perspective also explains why mass plays such a central role in gravity. Gravity does not respond to substance or composition. It responds to energy and momentum. Since mass is one way energy organizes itself, it naturally becomes a source of gravitational influence. Objects curve spacetime not because they contain a special heavy material, but because they represent concentrated, structured energy that must be accounted for in the geometry of motion itself. Even inertia, the reluctance of objects to accelerate, begins to feel less mysterious here. When you try to accelerate something, you are not pushing against an internal weight. You are asking an entire pattern of energy, interactions and field configurations to change all at once. The resistance you feel is the universe maintaining consistency. It is the cost of altering a stable arrangement, and this returns us gently to the question we began with. What is mass made of according to quantum field theory? It is made of interaction, of energy constrained by rules, of fields responding faithfully to change. Mass is not a substance hiding inside matter. It is the quiet signature of an active universe doing exactly what its laws require, moment after moment, wherever structure is allowed to persist. Following that thread a little further reveals another quiet layer. If mass comes from interaction, then its absence must be meaningful too. Some excitations move through the universe without ever acquiring mass, no matter where they travel. Light is the most familiar example. Photons remain massless not by accident, but because of deep symmetries built into the fields they belong to. In quantum field theory, symmetries act like constraints on behavior. They limit what kinds of interactions are allowed and which ones are forbidden. For the electromagnetic field, a particular symmetry prevents its excitations from ever gaining a rest mass. The field can ripple, carry energy, and transmit forces, but it cannot settle into a state that resists motion. As a result, light is always in motion. It cannot be slowed down or brought to rest. This contrast helps sharpen the meaning of mass itself. Mass is not the default. It is something that appears only when symmetries are broken or altered in specific ways. The Higgs field does exactly this. It reshapes the symmetry of space in such a way that some fields are allowed to resist change, while others remain free. Mass, then, becomes a marker of how symmetry is expressed in a given field. This also explains why the universe feels finely balanced. If all fields behaved like the electromagnetic field, matter could never settle into stable structures. Everything would rush along at light speed, unable to form atoms or bodies. If all fields were massive in the same way, motion would be sluggish and structure would collapse under its own inertia. The particular pattern of masses we observe reflects a universe tuned for persistence, not by intention, but by the logical consequences of its underlying rules. And so, mass, symmetry, and structure become inseparable. Where symmetry allows freedom, mass disappears. Where symmetry is reshaped by interaction, mass emerges. The universe expresses both with remarkable consistency, giving rise to a world that can move, bind, shine, and endure all at once, without ever needing mass to be a substance at all. There is one more layer where mass quietly reveals its character, and it appears when we look not at motion through space, but at change through time. In quantum field theory, every excitation has an internal rhythm, a way it evolves, oscillates and renews itself even when it is not moving from place to place. That rhythm is directly tied to mass. A massless excitation has no internal clock. It does not linger. It propagates at light speed and exists only as motion. There is no rest frame where it can pause and simply be. But a massive excitation is different. Even when it is perfectly still, it continues to evolve internally. Its field oscillates in time. That steady, unavoidable temporal activity is another expression of mass. This means mass can be understood as resistance not only to spatial acceleration, but to change itself. A massive field excitation cannot simply disappear or glide away. It must continuously renew its presence, drawing on energy to maintain its state. Time passes through it differently than through a massless wave. Mass gives matter a kind of temporal thickness. A single analogy can help clarify this without drifting away from the physics. Imagine a pendulum suspended in still air. Even if it is not swinging across the room, it has a natural tendency to oscillate if disturbed. That tendency reflects an internal structure that unfolds over time. A massless wave is more like a pulse of light flashing past, with no internal cycle of its own. In quantum fields, mass sets the pace of that internal unfolding. This deepens the idea that mass is not something added to matter, but something that shapes how matter exists moment by moment. It determines not just how objects move, but how they persist, how they endure through time, how they remain themselves from one instant to the next. Seen this way, mass becomes a quiet bridge between energy, motion, and time. It is the signature of fields that are allowed to linger, to oscillate, to hold their identity rather than rushing endlessly onward. And through that lingering, the universe gains memory, structure, and the possibility of lasting forms. When mass gives fields the ability to linger in time, something else becomes possible as well. Stability, structures that do not immediately dissolve, patterns that can repeat themselves reliably instead of washing away. Without mass, there would be motion and energy, but no lasting forms. A massive excitation can settle. It can occupy a region of space and remain there. It can bind with other excitations, sharing energy in a way that lowers the total cost of existence. This is how atoms form. This is how nuclei hold together. This is how matter becomes layered and complex instead of fleeting. Mass allows energy to pause long enough to cooperate with itself. In quantum field theory, bound states are not static objects. They are balanced negotiations. Fields interacting in such a way that change becomes expensive, not impossible, but unlikely. Mass plays a central role in this balance. It raises the energetic barrier to disruption. It makes persistence the easier option than transformation. A single image can help make this intuitive. Imagine a whirlpool forming in a flowing river. The water itself is always moving, but the whirlpool remains. Its persistence is not due to rigid material, but to a stable pattern sustained by continuous motion. Matter behaves in a similar way. Fields are always active, but mass allows their interactions to lock into repeating, self-sustaining forms. This is why the universe is not just a haze of radiation. It is why stars can burn for billions of years instead of flickering out instantly. It is why chemistry exists. Mass slows change just enough for structure to emerge without freezing it completely. It creates a middle ground between chaos and rigidity, and so mass quietly governs the pace of the universe. Too little, and nothing holds together. Too much, and nothing moves freely. What we observe is a balance where mass allows complexity without stasis, endurance without stillness, a universe where things can last but still evolve. As mass allows structures to persist, it also quietly determines how the universe bends around them. Gravity does not respond to solidity or composition. It responds to energy arranged in a stable, enduring way. And mass is one of the clearest signals that such arrangement exists in modern physics. Gravity is not a pull through space, but a response of space and time themselves. When energy is concentrated and organized, space-time curves. Paths that were once straight become gently redirected. Objects fall, not because they are pulled downward, but because they are following the easiest route through a geometry shaped by mass. Seen this way, mass does not act on space-time from the outside. It is part of space-time's content. It tells space how to curve because it represents energy that cannot disperse, energy that remains present long enough to matter to the shape of motion itself. This brings together many threads at once. The same confined energy that resists acceleration also reshapes the flow of time. Clocks tick differently near massive objects, not because time is damaged or distorted, but because the rhythm of change is influenced by how much energy is being sustained in one place. Mass affects time because mass reflects how intensely fields are active and constrained. A simple image can help here. Imagine a stretched surface supporting steady vibrations. Where the vibrations are gentle, the surface remains nearly flat. Where they are intense and persistent, the surface dips. Other vibrations passing nearby follow that curvature naturally. In the universe, mass marks where activity is intense and enduring, and space-time responds accordingly. This means gravity is not something added on top of mass. It is mass seen from the perspective of geometry. It is the universe accounting for where energy has settled into lasting form. And once that connection is made, mass appears not just as resistance to motion, but as a participant in shaping the very stage on which motion occurs. From the smallest particles to the largest galaxies, mass links quantum behavior to cosmic structure. It allows energy to endure, structure to form, and space-time itself to respond. Not as a substance pressing downward, but as a quiet, lawful consequence of fields, interacting and holding their patterns long enough for the universe to notice. As mass shapes gravity and stability, it also quietly answers a question we rarely think to ask. Why does an object feel like the same object from one moment to the next? Why does it persist as itself, rather than dissolving into motion and change? Mass plays a central role in that continuity. A massive system has a kind of self-consistency. Its internal activity is rich and energetic, but it is also constrained. The same patterns repeat, the same interactions recur. This repetition gives rise to identity. An electron today behaves like an electron yesterday, not because it carries a label, but because the field it excites has a specific mass and a specific way of evolving in time. Its behavior is locked into a recognizable rhythm. Without mass, identity becomes fleeting. A massless excitation has no rest frame, no internal clock, no way to linger as itself. It is defined entirely by motion. It passes through, interacts briefly, and moves on. Mass allows something to remain present long enough to accumulate history, to be acted upon, to act in return. This is why matter can remember, why atoms can store energy levels, why molecules can maintain shape, why complex systems can build on previous states instead of resetting each instant. Mass gives the universe a way to keep track of itself. A single image can help anchor this idea. Think of a melody played on a sustained instrument. The notes overlap, resonate, and reinforce one another, allowing a recognizable theme to emerge. A sharp, percussive sound, by contrast, exists only for an instant before vanishing. Mass gives matter sustain. It allows patterns to echo forward in time instead of collapsing immediately. Through this lens, mass is not just about weight or resistance, it is about presence, about the ability of a pattern to endure long enough to matter, to interact repeatedly, to become part of a larger structure. The universe gains memory through mass, and with memory comes complexity, continuity, and the quiet feeling that things are allowed to be themselves for a while. That sense of identity leads naturally to how mass becomes something we can measure at all. In quantum field theory, measurement is not about revealing a hidden object. It is about observing how a system responds when we interact with it. Mass enters every measurement as a quiet bookkeeping rule, ensuring that energy, momentum, and time remain consistent. When a massive system is probed, it responds in predictable ways. It accelerates by a certain amount when pushed. It curves space-time by a certain degree. It absorbs and emits energy in discrete patterns. These responses are not arbitrary. They are governed by the same field interactions that give rise to mass in the first place. Measurement does not create mass. It reveals how firmly a pattern is held together. This is why mass feels so reliable. Across experiments, environments, and scales, the same mass leads to the same behavior. That reliability comes from the stability of the underlying fields. As long as the rules governing those fields remain unchanged, the mass they express remains constant. The universe keeps score not by tracking objects, but by enforcing consistent responses. A simple image can help clarify this. Imagine tapping different musical instruments with the same force. Each responds with its own characteristic sound. The response tells you something real about the instrument's structure, not about the tap itself. In the same way, mass tells us how a system is structured internally, not what it is made of as a substance. This perspective explains why mass can be inferred even when particles are never seen directly. In high-energy experiments, physicists detect tracks, energies, and deflections. From these, mass is reconstructed as a pattern of resistance. It is a conclusion drawn from behavior, not a thing uncovered, and so mass becomes the universe's way of keeping its account balanced. It ensures that energy flows make sense, that motion remains coherent, and that interactions leave consistent traces. Mass is not hidden inside matter waiting to be found. It is written into how matter responds whenever the universe asks it to change. Even with all of this clarity, mass still holds edges that remain open. Quantum field theory explains how mass emerges, how it behaves, and how it participates in the universe, but it does not yet explain why the values of mass are what they are, why one particle is heavier than another, why the Higgs field couples strongly to some fields and barely at all to others. These numbers are measured, confirmed, and reliable, but their deeper origin is still being explored. This does not mean the explanation is incomplete in a troubling way. It means the universe is consistent without being arbitrary. The rules are firm, but their parameters invite further understanding. Physicists continue to look for patterns that might reveal why masses fall into the ranges they do, whether deeper symmetries exist, or whether additional fields quietly shape what we observe. What is striking is how constrained the situation already is. Change the masses of familiar particles even slightly, and the universe would behave very differently. Atoms might not form, stars might burn too quickly or not at all. Complex chemistry could fail to emerge. The fact that mass arises from interaction rather than substance makes this sensitivity understandable. Small changes in rules can reshape entire structures. This leaves mass in an interesting position. It is no longer mysterious in its nature, but still rich in unanswered detail. We know what it is doing. We know how it comes about. We know how it participates in stability, gravity, time, and identity. What remains is to understand why the universe chose this particular balance among many possible ones, and so mass stands as a bridge between what is settled and what is still unfolding. It is not an enigma hidden inside matter, but a visible seam where deeper structure may yet be revealed. A reminder that even the most familiar sensations, weight, resistance, presence, arise from rules that are precise, subtle, and still inviting us to look more closely. At this point, mass can be seen as something that quietly links the smallest and largest features of the universe. The same idea that explains why a proton resists acceleration also explains why galaxies hold together and why space-time curves around stars. There is no separate kind of mass for different scales. There is one principle, expressing itself wherever energy organizes and persists. At the smallest scales, mass emerges from fields interacting locally, from confinement, from symmetry shaping how excitations behave. At larger scales, those same masses combine, not by simply adding substance, but by layering organized energy into increasingly complex structures. An atom, a molecule, a planet, a star. Each level carries mass not as a new ingredient, but as accumulated persistence. What is striking is how smoothly this carries upward. There is no sharp boundary where quantum behavior hands off to classical weight. The resistance you feel when lifting an object is the collective expression of countless quantum field interactions acting in concert. Mass scales because interaction scales. Stability builds on stability. This is why quantum field theory does not feel remote from everyday life once it is understood this way. It is not describing an exotic realm disconnected from experience. It is describing the same resistance, the same inertia, the same weight, traced all the way down to its source. The familiar feeling of heaviness is the macroscopic echo of microscopic rules being followed with extraordinary consistency, and so mass becomes a unifying concept rather than a dividing one. It connects motion to structure, energy to endurance, quantum rules to cosmic architecture. It does not sit at one level of reality. It threads through all of them, quietly ensuring that what begins as a small local interaction can grow into something that shapes space, time, and experience itself. From this perspective, the universe feels less like a collection of layers stacked on top of one another, and more like a single coherent system, repeating the same logic at every scale. Mass is one of the ways that coherence makes itself felt, not loudly, not dramatically, but reliably, wherever the universe allows patterns to last. As this understanding settles, it becomes clear why mass feels so immediate and undeniable in everyday life. Of all the deep physical ideas, mass is the one your body encounters directly. You do not need instruments to sense it. You feel it as effort, as strain, as the time it takes for something to respond when you push it. That immediacy is not accidental. Mass is the way the universe makes its underlying rules tangible. When you push an object, you are not pushing matter alone. You are pushing against an entire web of field interactions that must reorganize together. Electromagnetic bonds resist separation. Confined energy inside nuclei must be accelerated as a whole. The Higgs interaction continues to enforce inertia. All of these contributions add up in the single sensation of resistance. Your muscles register the cost of change directly. This is why mass feels different from other properties. Color depends on light and perception. Temperature depends on motion averaged over time, but mass confronts you instantly. It announces itself the moment you try to alter motion. In that sense, mass is the most democratic of physical quantities. It makes the abstract structure of reality accessible to touch. There is something quietly elegant in that. The deepest framework we have for describing nature does not hide itself entirely behind mathematics and instruments. It reaches out through mass and lets itself be felt. Every time something resists you, quantum fields are doing exactly what they are supposed to do, and your body becomes the measuring device. This helps explain why mass has played such a central role in physics for so long. Long before fields were imagined, mass was already guiding intuition. It hinted that motion had rules, that change had a cost, that the universe was not frictionless or arbitrary. Quantum field theory did not replace that intuition. It fulfilled it. It showed that the resistance we feel is not a surface illusion, but a faithful expression of how reality is organized at its deepest level. And so, mass closes a quiet loop. It begins as a sensation in the body and ends as a principle woven into fields that fill all of space. The same idea links your hand, lifting an object to the structure of the vacuum itself. Nothing extra is added, nothing mystical is required, just interaction, energy, and the patient consistency of the laws that allow patterns to endure. Between the deep structure of fields and the final sense of meaning, there is one more place where mass quietly does its work. It meets us at a scale our bodies can understand. Mass translates the abstract rules of quantum fields into forces our muscles can feel, into rhythms our balance can adapt to, into a world sized just right for living systems to exist within it. If mass were much smaller everywhere, motion would dominate. Objects would drift, slip, and respond too quickly for stable interaction. If mass were much larger, change would be slow and unforgiving. Movement would demand too much energy. The universe would feel either ghostly or immovable. Instead, mass sits in a narrow range that allows touch, effort, learning, and coordination. It allows a body to predict how things will behave when pushed or lifted. It allows trust in cause and effect. This is not because the universe was designed for bodies, but because bodies are arrangements of mass that could only arise in a universe with these particular balances. Our nervous systems evolved inside a world where resistance is reliable, where acceleration has a cost, where momentum carries meaning. Mass is part of why experience itself feels continuous rather than chaotic. A single image can help anchor this. Imagine trying to live in a world made only of mist, where nothing ever pushes back, or in a world made only of stone, where nothing ever yields. In both cases, interaction collapses. Mass gives the world a usable texture, not too loose, not too rigid, just resistant enough to support action. In this way, mass is not only a physical concept, but a bridge between scales. It allows quantum rules to become lived reality. It allows fields to become floors, tools, and hands. Without changing what it fundamentally is, mass becomes the reason the universe is navigable. Why it can be explored not just with instruments, but with bodies moving through space, learning the rules through touch and effort, one interaction at a time. And with that in place, the final understanding can arrive gently, not as an abstraction, but as something already felt and quietly familiar. As everything we've explored settles together, the question we began with finds its answer in a surprisingly quiet place. Mass is not a hidden substance tucked inside matter. It is not a fundamental heaviness sprinkled onto particles. It is the steady consequence of interaction, of energy that cannot simply pass through, but must remain, circulate, and respond. According to quantum field theory, mass is what happens when fields resist change, when motion costs energy, when patterns are allowed to persist rather than dissolve. Sometimes that resistance comes from a background field like the Higgs. Sometimes it comes from energy tightly confined inside composite particles. Often it comes from many effects layered together so seamlessly that they feel like a single property. But in every case, mass is not what something is. It is how something behaves. This way of seeing gently reshapes the world. Objects around you are not heavy because they contain weight as an ingredient. They are heavy because they are active, because countless quantum processes are being sustained in balance, because changing them would require reorganizing energy that has settled into stable patterns. What you feel as weight is the present expression of that stability, and there is something calming in that realization. Nothing is burdened by mass from the outside. Nothing carries unnecessary heaviness. Wherever mass appears, it appears because the universe is doing something coherent and lawful there, holding energy in place, allowing structure to endure, letting time pass in a way that leaves traces behind. So when you encounter mass, in an object, in your own body, in the pull of gravity itself, you are encountering the universe being consistent with itself. You are feeling the cost of change in a reality built not from solid things, but from relationships that persist, from fields that respond, from energy that, for a while, is allowed to stay. And in that sense, mass is not a mystery at the center of matter. It is a quiet agreement the universe keeps everywhere, a way of ensuring that motion has meaning, that structure can last, and that the world can be felt as real, present, and gently resistant to change.